Okay, well, welcome back. This is the second and probably final segment for section 4.2, sorry, 4.4. And as you recall, we were in the process of graphing the cosecant functions. We had graphed one example of a secant function that had both a vertical stretch, a modulation to its period, and a vertical translation. So we're going to probably do one with secant in this segment, cosecant, and then I'll probably give a couple, maybe one or two examples of taking a graph and producing an equation. So let me move over here to the document camera, and I think I'm just going to pick up right on the same page that we were on previously, since I've got half of it left. So as you recall, we had graphed this particular secant function. And notice there's not a whole lot of detail in this graph. Really, the only thing that was critical was the location of the vertical asymptotes and these specific high and low points to be able to do this effectively. So let's try another graph. So let's say graph the function y equal to, we don't do many with negative signs in the a value. So maybe let's try one. So let's do negative 1/2 cosecant of x over 2 plus pi over 2. Yeah, let's make it pi over 4. Okay, and then maybe we'll add 1/2. All right, so we got some fractions in there, we got some negative signs, we got all kinds of good stuff. Okay, so the first thing, just like we've done previously, when you have a non-b value with the vertical or horizontal shift, you have to do this factorization first. You don't have to, but it really does keep things organized. So we have negative 1/2 cosecant of 1/2 is the quantity I'm factoring out. And so I'm left with x plus pi over 2, then plus 1/2. Okay, so let's consider what's going on here. There's a couple key features. First off, we have a modification to the vertical stretch shrink. It is reflected. We also have sort of an oddball vertical shift. Notice it is shifted not to the right, but actually to the left. C is actually negative pi over 2 here. D is 1/2, and we have a B value of 1/2. So maybe sort of simple, we'll kind of do it in the same vein. We'll start by drawing it, and then we'll figure out the P and all that sort of stuff. So the first thing to do is to draw a cosecant function without any axes. So I'm going to start with vertical asymptotes, as we've done previously. Okay. Maybe put a couple of them in there. So I'm gonna be drawing this graph for 2 complete periods. Yeah, let's make it 2 complete periods. So I need 1, 2, 3, 4. Okay. And I think the book sometimes asks you to do 2 complete periods. I'm not sure why, but I suppose there's some value in it to see everything stretched out. Okay, so the only thing that I'm going to do a little differently is I'm going to reverse the order. Here we had sort of this sort of positive value. Well, it's not really necessarily positive, but I think you get what I'm saying here. You have the upward turned region, then the downward turned. They're not necessarily positive or negative, but they do blast off to positive infinity and down to negative infinity, etc. So the reason that I'm shifting this up is because of this negative sign. Because there's a negative sign, I know that the whole thing should be sort of reflected across the x-axis. But that reflection occurs before all of these translations. I want that to be clear. And that's sort of something that sometimes throws people off, because it's like, well, which part do I do first? Well, normally I would say leave all that stuff alone and figure out C and D. But the thing that you do want to recall is that the graph is going to be reflected. So rather than being in this blasting off to positive infinity, it's actually going to be blasting off to negative infinity. So that's really the only difference I'm going to do in graphing this. So I'm going to start with sort of a region that turns downward, and then a region that turns upward, and then repeat. And repeat. Okay, so recall that the normal origin for cosecant is coincident with the vertical asymptote, and will fall halfway between the sort of upper branch and lower branch. That's the normal, the normal origin. And notice I'm starting before I have one that goes downward, right? Whereas normally, if you recall from the way secant looks, the very first sort of segment will be a piece that goes vertically upward. So that's why I'm picking this location right here as my normal origin. I could just as easily have picked this location. It really, or even this one. It doesn't really matter. But you know, I like to have things sort of in the positive have positive x coordinates, but you know, that's just personal preference. So what we know about this point is it has a coordinate of c comma d, which is negative pi over 2 comma 1/2. And I can maybe put that off to the side here. So negative pi over 2 comma 1/2. And that's this coordinate. So the cosecant function will be, normally would be 1 unit above and 1 unit below this sort of baseline. But because the magnitude of A is 1/2, it will only be 1/2 unit above and below, above and below. So based on the fact that this has a y value of 1/2, half a unit upwards is actually 1. So this, the x value, or sorry, the y value of this low point is 1. Similarly, for the, actually this kind of, my perspective is a little weird. This point should probably be a little bit closer to here, somewhere halfway between, so it looks a little better. But anyways, so this local maximum will be 1/2 minus 1/2, or 0. So the y value will be 0. So this tells us that the x-axis is coincident with these, or touches these graphs at their local maximum. Okay, and that this unit would be 1. So once we get the y-axis in place, we can put that there. Okay, so now let's talk about the period. So because b equals 1/2, the period will be 2 pi divided by 1/2, which is 4 pi. Okay, well, that tells us that each two of these it has a distance of 4 pi between them, horizontally speaking. So if we were to add 4 pi to this one's x position, this will be some bizarre unit of, gosh, 4 pi is 8/2, so this will be 7 pi over 2. And if we back it off to just half a period, that would be 2 pi, so this will be 3 pi over 2, which tells us, since we're at minus 1/2 pi, 3 pi over 2, halfway between that would be pi over 2, and then 1/4 of the way would actually be our x value of 0. So it turns out that the y-axis is 1/4 of the way between these two successive vertical asymptotes. I'll try to capture that here. And maybe it would be easier just to, I don't even know. I mean, you have to put some sort of horizontal ticks in here somewhere. So maybe we just pick this one, which we figured the first time, which is 7 pi over 2, and then adding 8 more pi, 8 halves pi to this, we end up with 15 pi over 2 right there. And so that is, it's not a great graph, but it's sufficient for what we're trying to do. Now, one thing that I do want to point out is that in the text, they never give you these vertical asymptotes. They never draw them. It's a drawing tool that maybe these authors consider to be a little juvenile, but I think that they're critical to be able to see what's going on. And so they do have some value, in my opinion. But it may be kind of hard for you to figure out when you're looking at a graph where those things are happening, right? So you may not be able to distinguish, oh, this is the point. So how do you do that? How do you figure out where these vertical asymptotes are? Well, here's what I do. I know that they're occurring halfway between this upper and this upper branch and lower branch. And if I can figure out where these points are located, that's all I really need to be able to complete the sort of taking a graph and finding an equation. The same thing could be true for cotangent, where you find that reflex point, which is kind of the center of the graph. The vertical asymptotes have to occur halfway between successive reflection points or reversal points. Okay, so anyways, this is kind of a little digression. What I'd like to do now is, and because it leads right into this last idea, what I'd like to do now is to actually take a graph and produce an equation from it. Maybe we have enough time to do two of them just for the sake of completeness. So this is section 4.4. I think we're on page 3. We don't make a lot of pages because we just make a graph and talk about it. So let me just start by graphing something. Graph at least a period and a half of a secant function, or maybe cosecant, whatever. And since we've developed quite a bit, what I consider to be hopefully quite a bit of skill in this graphing, I have no compunction about making these somewhat challenging. So let me just kind of put the x-axis in here, and let me make the y-axis, oh, I don't know, let's say it's right here. And then I'll put some points on here. Let me make this like 10. And maybe make this out here 15. Now this one's going to be quite challenging. And the reason it's going to be challenging is because we have to kind of make some guesses here. I know my graph is kind of squished down here, but whatever this value is, we'll focus on this one's low value and this one's high value. This one should actually probably be up a little bit. It's just because of the perspective. As I'm looking at this page, I tend to make things kind of sandwiched together there. Okay, so if you were to have this is your graph and be told to produce the equation for it, you will necessarily need to have some information about what kind of function it is. So I would say this is a secant function. Okay, produced, and the directions might say write the equation of the following graph, etc. There's other ways to say that, but they all mean basically the same thing. We need to find A, B, C, and D. So first off, what we will need to do is we will, and sometimes they're pretty succinct about saying that you need to have C be the least positive value. And they may say something about reflections or whatever else. I mean, we don't need to get into that too much, but in this particular case, let's use that specification that we'll find the least positive value of C. So if it's a secant function, remember the normal origin occurs below this sort of upward branch at its lowest point. So splitting the difference here, we know that that's C and D, and it's the least positive value of C, because this one's actually going to be a negative So all we really need to do to find C and D is figure out what that coordinate is. So maybe the one, remember I said this one's kind of a little bit goofy. So one way to figure out what its D value is that it's the average of these two. So looking at this graph, I'd say more or less that this is at a Y value of 7, and that this one down here might be at a Y value of, if that one's down 3, that one's probably up 3. I think it's at a Y value of 3. So the average of those two is actually going to be 5. I don't know its X coordinate, but I'm going to say by just inspection that its Y value is 5. Looking at this axis, I think it's fair to say maybe if we break this up into thirds, I think that's about a third, and maybe that's a third. So this would be 10 and 5. And notice this seems to coincide pretty well with that point. So I think it's fair to say that that's about 10. So from the graph, we have that C comma D is equal to 10 comma 5. Okay, so the next step is to figure out what the B value is. And remember, to find the B value, we need to find the period. The period is going to be the distance between two successive vertical asymptotes. So this right in here, and I'm going to leave an equal sign. There's the period, whatever it happens to be. Now, just guessing, I'd say that this one probably occurs at an X value of 1, and that this one, that's pretty close to 2.5 or 12.5. It's going to make the math a little bit challenging, but I'm just going to say 11.5, and since I probably want it in a fraction, I'm going to call this 23 over 2. Okay, so based on this, recall that B is going to be equal to the normal period divided by the actual period, which for secant, the normal period is 2 pi, and then we're going to divide it by 23 over 2. So we get this really weird number, which is 4 pi over 23, and that can't be reduced, right? So what do you do? Finally, the A value is going to be the difference between the baseline and the Y value of the first either positive or negative branch. And so I think it should be pretty clear from just the numbers we have here that A is equal to 2. And that's almost always how it works with A values. There isn't some big complicated equation or something to write. It's almost always just by inspection. So in this case, A is equal to 2. And so now to write the equation, we have Y is equal to A value, which is 2, times secant of 4 pi over 23 times X minus 10 plus 5. And so more or less, just by some guesstimation on our part, that is the equation of this function. If we had been told that it was cosecant, there would be some slight modification, but the A value, the B value, and the D value would be exactly the same. The only difference we would have is there'd be a slight shift in the C value. So let's do one more involving cosecant instead of secant this time, just so we can see the similarities and the differences. And then I think this will be it for us. So this is section 4.4, page number 4. So let me start again by drawing a sequence of successive vertical asymptotes. Okay, then I need to put a X and Y axis in there somewhere. So let me just do this. How about my x-axis and maybe put my y-axis there. And I'll do it similar to what I did last time, but maybe I'll make it a little bit harder here. Let me call this 5, -5, and make this, oh gosh, I don't know, let's make that 4 pi. Okay. So where do we even start? Well, if we want the least, this is a cosecant function. Okay, so again, this is going to require a little bit of estimation on our part, because it's not necessarily clear-cut what the coordinates are of our critical points, so we have to just sort of guess a little bit. I mean, it's an educated guess. It's not just completely out of left field. So let's start with this. We have to kind of get some closer stuff in here. So notice that the distance between 4 pi and this vertical asymptote looks a bit larger than the distance between the y-axis and the vertical asymptote. So the y-axis, or the value of 2 pi should be about here. And I would argue that maybe this is 3 pi. Call that pi. And so I'm gonna just go out on a limb here and call this, looks like maybe that's 1/3 of the way. So I'm gonna call that x coordinate pi over 3. Looking at the upper and lower points, the minimum and local minimum and maximum, based on this scale here, I'd say that that's more or less 7, and that this one down here is -2. This is sort of going into my thought process. I have to figure out sort of distance between these two and those sort of like physical features that are on the graph to be able to produce this stuff. So recall for cosecant, the normal origin occurs vertically halfway between the upper and the lower branch. So right about sort of in here. We can be a little more precise. And it occurs at the first vertical asymptote with a positive branch after it. Okay, so this x value, whatever it happens to be, is in fact the least positive value for C is sitting right here. So somewhere in between here, I'm just going to kind of make a little x. Okay, so now we have to be a little more precise than just sort of like, well, estimating where that is, because we know that this point occurs halfway between this one and this one. So if we just real quickly did a little calculation, C is going to be equal to the average of the upper value and the lower value. So we have 3 pi plus pi over 3 divided by 2. And so we'll simplify this fraction. We'll multiply everything by top and bottom by 3. So we have 9 pi plus pi over 6, right? Everything multiplied by 3. So this becomes 10 pi over 6, or 5 pi over 3. Okay, so that gives us a precise way of finding that x value. What about the y value? Well, that's D is going to be the average of the upper and lower sort of max and min points. So this will be 7 plus a -2 divided by 2, which is 5 over 2. There's no need to reduce it anymore. What about the, so that gives us C and D. We did it a little different than we've done it before because it was not trivial to find just the coordinate of that point. What about the B value? Well, the B value is going to be based on the period, and the period is the distance between these 2 points. So let me start by writing the period is 3 pi minus pi over 3, which is equal to 9 pi over 3 minus pi over 3, which will be 8 pi over 3. And now that we have the period, we can find the B value. So B is equal to the normal period over the actual period, which is 2 pi divided by 8 pi over 3. The pi's will cancel, and you end up with 6 over 8, which is equal to 3 over 4. Not bad. What about the A value? Well, the A value is going to be equal to, pick any one that you want. You can just take the difference between the local minimum and the D value to find that. So A will be equal to 7 minus the D value, which is 5 over 2, which equals 14 over 2 minus 5 over 2, which is just 9 over 2. Okay, so now we have A, B, C, and D. It took a little more work than maybe that we're used to, but it's all basically the same process. You know, we select a few points that are recognizable, we try to line things up, and we go C, D, B, A. This is pretty much universal. You can switch these two, but getting this C and D first is kind of critical. So to finish this off then, Y is equal to the A value, which is 9/2, the function times the function, which is cosecant, of the B value times X minus the C value, which is 5 pi over 3. Close all those parentheses, and then add the D value, which is 5/2. And there we have it. Okay, so to finish this off then, as I said, there's not a whole lot of use for this sort of graphical techniques. It's more of an academic exercise, which is fine. And for completeness, now you should be able to graph every trigonometric function with any kind of transformation or translation, and also be able to take a graph of any of those functions and produce an equation. I say an equation because the C values can shift, or the functions themselves can usually shift because of the two pairs are in some sense interrelated. We could very easily write this as a secant function. We just have to change the C value. Okay, well, I don't want to get too long-winded here. So this is the end of both section 4.4 and also the end of chapter 4. I will see you again in chapter 5.